Time to play that?
Plead the fifth.
I don't think I know.
You don't incriminate yourself.
I see. Yes. Is it plead the
Plead the fifth.
fifth? FITH?
Fifth.
Yeah, I don't think I. Okay.
Fifth Amendment.
Oh, fifth.
Fifth.
Oh, FIFP.
FIFP.
Okay, I was getting that. Okay.
It's hard to understand the mask. Sometimes.
Oh, yeah, so there's a small change that I set this before. That's Michael. Oh, it's already set. That's it. All right. Yeah, so there's a small change of plans. So the homeworks are going to be due in the reverse order. What's that called? When planets go in the
Retrograde? Retrograde?
yeah, retrograde. Retro movement. Opposite direction. That's something to say that you first see homework 6. That's due March 15. Tuesday. And then comes homework 5, which I postpone 5 a day. Oh, sorry, 2 days. Next class. So that I have more time to spend on it. It's on small angle approximation. I can do it quickly. I was planning to do that in a hurry today, but then I realized it involves Fourier transform. So some of us might be not so comfortable with Fourier transform. So a little slow might be okay. So. And there is midterm 2. Yeah, we did an example on a simple pendulum. Again, you must have seen this course before. The expectation is that you're aware that there's plenty of problems you can work on with this technique, but I'm only touching on the simplest one in principle. But the idea was that you have a very good understanding of simple pendulum in our normal day-to-day knowledge, so you can connect with the new concepts. That's why a simple example sometimes is useful for learning things better. You should explore new examples. You should be able to do those things. And another next level in development would be a double pendulum. Again, have you guys seen a double pendulum in a video or something? So maybe try a video, right? Since we have this computers these days. It's usually interesting. Like it's pretty much pendulum also, right? Normal pendulum, there is a non-triviality in the fact that first of all, the time period is not constant when you have large amplitudes, but then the time taken has this non-triviality that it approaches infinity as angle goes to pi. So even single pendulum is slightly non-trivial. Similarly, double pendulum is trivial when you have small angle approximation. So let's see, first actually talk about two things simultaneously.
Okay, first let's see a double pendulum video and then we'll come back to it. Are we going to YouTube first and then doing this? Videos. Yeah, why not? This 2.29. Completed. I think it's understood. I don't think he's going to do another initial condition. Okay. So that's a double pendulum. And looking at the motion, do you expect it to be having an analytic solution? Probably not. It was too complicated, probably to be captured in using the standard. So it is true that you do not have analytic solution for the double pendulum. So then we again do the small angle approximation, and then even that has a lot of richness in it. And we will see how it can. We won't go there, but in principle, it can imitate a two-level atom. Like two-level atom has this one energy level, which is higher than the ground state, and that's two levels. And how you can jump from one to the other and coming back. That's a simple mechanism. And double pendulum will have two fundamental frequencies. Two fundamental frequencies can be thought of as the two energy levels of an atom. And then you can say, okay, how it goes from one state to the other state. It's going with one frequency to the other, and what is the probability. So it has a modeling there, but we won't go into all that. What we will be doing here is that just find the two fundamental frequencies and get the motion. And so then analyzing the motion is where you come into the going from one to the other. We won't be doing that here. So yeah, so that's why did I should also point out when it is so chaotic here. Have you heard of the word chaos? That's a subject in itself. So what is chaos? The field of chaos, maybe? Classical mechanics has it's an immediate extension of classical mechanics. It's called nonlinear dynamics. Maybe that's the way you call nonlinear dynamics. So how would you define chaos, chaotic systems?
Eigenproppen?
increasing entropy or multiplicity?
No, that's very, no, I would say no to it, because that's very predictable. Every system you take will always try to increase its entropy, right? That's what actually we see around us, that there are two things that govern our whole nature, apparently. One is energy has to be minimized, and entropy has to be maximized. These two principles pretty much govern everything. We understand the energy part much better than the entropy part, but these two principles apparently explain everything. But it's always the same, right? Entropy is always increased, so it's predictable in that sense. So it's not chaotic. Chaotic is when you cannot predict things. And then you ask, can you have such a system at all? It is not predictable. Newton says that you give me the initial conditions, you can get give my life the initial positions and velocities of every atom in my body, and then I can predict my whole life in a sense. So can Newtonian mechanics have such a system where it cannot predict? Newtonian physics is predictable, right? Very deterministic. That's the word you say, deterministic. So can you have chaotic system in principle?
We can have a quantum system.
True, quantum, quantum system is surely an example, but I think we want to stay out of it, so let me motivate that. Yeah, good point. So what you're trying to say is that what Newton says is that mass times second derivative of x, let's stay one dimension, right? X as a function of time is F, right? So give me the force, give me the, so that if you can solve this differential equation, if this is given to us, we can solve x as a function of time. And x as a function of time, and this is plus initial condition, right? Plus x of 0 plus velocity of 0. Right? So give me a differential equation, initial conditions, right? You can get position as a function of time for any time you want to, right? That's Newtonian physics in very simplistic terms. What quantum mechanics now does is that, quantum mechanics says that, that's not possible, right? Because x of 0, comma, momentum, like x comma p, like mass times velocity, like commutation relation is equal to what? IH bar. So these two you cannot specify simultaneously, right? So you lost this initial condition right there, right? Because quantum mechanics says you cannot measure these two accurately enough. So since this cannot be measured accurately, this cannot be known accurately. So if you are sending a spacecraft to Mars, because you don't have your initial conditions correctly, because quantum mechanics says that you cannot specify it properly, so you will make an error in reaching that. So instead of Mars, you might reach, let's say, on the horizon of, what do you say, very close to Mars. But it's not going to happen that if you shoot a satellite from here with a small error, instead of Mars, you will end up in another galaxy. And you'll be close to Mars. So quantum mechanics will still say that it's not completely deterministic, but probably there's a good chance that you'll be close. Right? But what chaos is that instead of reaching Mars, you might end up in another galaxy. Right? Often you explain this by you say that a butterfly flaps its wing in Brazil, and we have a tornado in the United States just because exactly because of the butterfly flap its wing. So that's like saying that you do something here and you didn't want to, but in another galaxy suddenly magically something happened. And then you say that, is that possible at all? Right? And that's chaos. Right? That's small. You change the initial condition by tiny bit. You make a small error in this initial condition, but the change in this 10 minutes later might be too off. Like it's not a small change. Like for example, this is your trajectory. That's a predicted trajectory. You make a small error here, expectation is that you will go here. It's still continuously reaching. But chaos means that instead of here, it just breaks off here and goes somewhere there. Like there's a discontinuity in the curve itself. And the question is that possible at all in Newtonian physics? And the answer is yes, it can happen. Most of the time when we work with Newtonian physics, we don't realize this because we work with linear differential equations where superposition is very inbuilt in that. But non-linear differential equation, that's when as simple as instead of harmonic oscillator potential, which is x squared or times r, you go to x cubed. And that becomes, it is very rich then, and it has non-trivial features like this. Like even x cubed, like whatever we saw there, right, that has chaos in it. Like that motion that you were saying, you change the initial condition a little bit, you won't see that mechanism at all. You'll see completely entirely different form of motion. So double pendulum at large angles shows chaos. Single pendulum, I'm sure. Yeah, quiz, right? Does single pendulum for large, for surely for small angle, you don't have it because it's simple differential equation, correct? But it is non, so the question is, does simple pendulum exhibit chaos for large angles? That means to say that you change the initial condition a little bit, very tiny, like infinitely tiny change in initial condition changes your prediction dramatically. Right? Okay, so that's basically the concept of chaos. So kind of neat, I think. Yeah. Okay, so that was digression. So let's talk about double pendulum at a very linear level. To talk about small angle approximation. So a double pendulum is like we said earlier. So this is your ceiling, let's say, and you have a mass m1 attached. Again, we say that these are two simple pendulums, right? I think Rob had clarified that simple pendulum, simple part very nicely. That the string is rigid but massless, so everything is related to this point here. So let's say this is L1 and that's M1, right? And that's angle theta 1. And that's a line extending to that point. And again, as a reference line, let's say the second mass is like this in general. Oh, it's L2, and this is theta 2. You again assume everything is happening in a plane. In principle, again, you can make it a spherical double pendulum, but double pendulum in a plane itself has nice features, so we'll stick to this. We want to write the Lagrangian for this. Now we have, last time what we did when we were doing simple pendulum was that first we tried to write the Newtonian equation for that and then came back to this. Here there will be two tensions, right? T1 and T2, more work, and we realize that Lagrangian doesn't deal with the tension forces at all. It's nicer, easier. So let's immediately go into the Lagrangian formula. So it's clear, the first point in when you're doing Lagrangian is to get the coordinates clear. Which coordinates do you want to keep, right? If one possibility is that you write x1, y1 for the coordinates for m1 and x2, y2 for the coordinates for mass m2, but it's clear that there is a constraint that x1 squared plus y1 squared is equal to L1 squared. And similarly, x2 minus x1 squared plus y2 minus y1 squared is equal to L2 squared. So there are constraints here. So the four coordinates are clearly not the ideal situation, so we should choose better coordinates. And in this case, this is reasonably straightforward to realize that it is θ1 and θ2. But often in complicated systems, that might be the most challenging situation, as to figure out which coordinate do you want to work with, which is a dynamical variable. That could be in itself a challenge. So the first point is dynamical variables are generalized coordinates, right? Let me say generalized coordinates or dynamical or both dynamical variables, or you mean generalized coordinates. Is θ1 and θ2, which means that you're looking for a Lagrangian which depends on θ1, θ2. You can have the velocities related to that. So θ1 dot, θ2 dot. Right? That's clear derivative of θ1 with respect to time. How does it move? And in general, it could have time also. It generally has the time dependence when you're, I think I asked this as a quiz problem, that when is the Hamiltonian an energy? Is Hamiltonian always an energy? And you say that, oh, that's not always energy. Sometimes there are certain examples that you guys give. One very simple way to see it is that if the energy of the system is conserved, that means there shouldn't be any input of the energy. Right? So if energy is constant, so if there is no input of energy, energy will be conserved. And one very simple way of seeing it is that there should be no time dependence in the Lagrangian. Right? That's as of now, I'm just saying it as based on experience, but later we will see that under what conditions is Hamiltonian energy, it will come out to be that time dependence should not be there. So we'll come to that later, but keep that in mind. Here it's a closed system. We are not pumping in any energy, right? So that will be like, that is gravitational force acting, but then there is a potential energy associated with that. So in that sense, there is no external energy being pumped. What will be an energy being pumped? We did an example of inverted pendulum last time. There I was oscillating the base, right? That is my hand oscillating it, but then I'm not writing the potential energy for that force. So that's an external energy that's contributing. Talking about inverted pendulum, I should mention that Aryan pointed out that I made an error in the expression for the inverted pendulum formula at the end of the lecture last time. I was doing it in a hurry, so there was an algebra mistake in the very last step. Correct? Last step, right? So refer to Aryan, right? That thing. Is that okay? Second quiz. Right? Second quiz is that correct the equation of motion for the inverted pendulum in the last lecture. Right? So I had put a Lagrangian there. So L was correct. L was correct. Right. Then there was then I did dL by dV. This had an error in it. Okay. So I forgot to take the derivative with cosine function. That's the error, right? Forgot derivative. With cosine function, and dL by d, what was it, theta, I guess, right? That was correct. And that was correct. And so basically get the equation of motion. Okay. So that should be just to correct that. I mean, just so that we are doing correct things. Okay. So why did I go into? Yeah, I was pointing out that as time dependence usually has to do with the conservation of energy, and in the inverted pendulum is an example where you supply energy from outside, and there time dependence shows up. There it's Hamiltonian is not the energy. In this situation it is, but later on we will, in next week basically, or next couple of lectures, we will figure this out explicitly. Okay, but here, what's the Lagrangian? That's our goal. And to go around that, we know that this is equal to kinetic energy minus potential energy. That's how you proceed with that. But kinetic energy is given in terms of velocity, so we want to write down our coordinates in terms of angle theta. So let's go with x1. So x1 is equal to, x1 is down here, so that's L1 sine theta 1. And y1 is equal to minus L1 cosine theta 1. X2 is equal to, x2 all the way here, so that's L1 sine theta 1 plus L2 sine theta 2, and y2 is equal to minus L1 cosine theta 1 minus L2 sine theta 2. Is that right? Yeah. Okay, so we are interested in the velocity, so we need the time derivative of x1. So let's write dot representing the time derivative, x1 dot. L1 is a constant, so it's only theta 1 dot, so it is L1 theta 1 dot and cosine theta 1. Y1 dot is equal to minus plus L1 theta 1 dot sine theta 1, and x2 dot is equal to L1 theta 1 dot cosine. Two, y2 dot so that should be clear. Square this, that's your kinetic energy. So how do you do this? So let's say kinetic energy, or this square plus kinetic energy is equal to half m1 x1 dot square plus y1 dot square plus half m2 x2 dot square plus y2 dot square. So that's equal to half of m1 x1 dot square is here, right? So, and I have to do y1 dot square. So that's clearly, when I square this, there's a square of this, so that's L1 square theta 1 dot square. But I'm doing it in my head, cosine square plus sine square theta. So that's this term completely. x2 dot square plus y2 dot square. I have to square this and square this. So there is clearly square of this plus square of this. So that's L1 square theta 1 dot square. Oh, what am I doing wrong? Mistake is that this is here, right? The masses are different. So this is plus half m2. This is L1 square theta 1 dot square. That's here. plus L2 square 2 dot square, because square of this again cosine square theta 2 cosine square theta 2 is 1. And then there are cross terms, right? So it is plus 2 L1 L2 theta 1 dot theta 2 dot, right? And there is cosine theta 1 cosine theta 2 plus sine theta 1 sine theta 2. So this gives you an expression like cosine theta 1 cosine theta 2 plus sine theta 1 sine theta 2. That's a cross term, but that's trigonometrically cosine of theta 1 minus theta 2. So this is cosine of theta 1 minus theta 2, or theta 2 minus theta 1, doesn't matter. That's your kinetic energy. Any questions there? Okay. Questions on the algebra?
Shouldn't the term, the first expression in kinetic energy, shouldn't the individual x dot 2 and y dot 2 be squared and not the sum?
Oh, the first expression. Yeah, I
The
see.
first-
Oh, yeah, here, right?
Yeah.
Oh, yeah. That's the confusion. Sorry. Yeah, that's of course. Yeah, so, yeah, that was my bad. Yeah, that can throw off everyone. Questions? Okay, if that's the case, then we have, that's kinetic energy. We have the formula there. We have potential energy. Potential energy is M1 G times Y1, like how high you are, plus M2 G times Y2. That's your potential energy. But I want to write everything in terms of theta 1 and theta 2. So Y1 is minus M1G L1 cosine theta 1. And this is minus M2G L1 cosine theta 1. And then we have minus M2G L2 cosine theta 2, which is probably best written as minus M1 plus M2G L1 cosine theta 1 minus M2G L2 cosine theta 2. Oh, I didn't move the camera, right? No one's but the levels not telling me. Okay. 6. Okay. No. Okay, so Lagrangian is the sum of these, or difference between these two. Before we do that, we can add these two terms, right? They come together. So it is half of M1 plus M2 of L1 theta 1 dot square, taking care of these two, and half of M2 theta 2 dot square, and then let's say there is a cross term which is M2 L1 L2 theta 1 dot theta 2 dot cosine of theta 1 minus theta 2, and potential energy is plus, right? So I'll subtract that. Plus. Okay.
The first L1 is square.
L1 square, yes, and here probably is an L2 square. Thank you. Okay. Okay, thank you. Okay. Let's write this in the following manner. Let me call L1 is equal to. So let me call L1 is equal to this plus this. That's L1's. What does L1 look like? This should ring a bell. Suppose rest everything is not there, it's just L1. What does the system represent?
Like one single pendulum with two masses.
Very good. So it is a single pendulum of length L1, but the mass is M1 plus M2. If you look into the simple pendulum Lagrangian, that looks exactly like this. So that means that's a motion of one pendulum, but out of mass M1, it has the baggage of this M2 also. It has to drag M2 also, so it looks like that. What about L2? So that's a piece inside. Let me recognize another piece. So it's M2, L2 squared, theta 2 dotted square plus M2G L2 cosine theta 2. That's again a simple pendulum, but of mass M2 alone and of length L2, right? That's this simple pendulum. If this was fixed, that's the motion of that piece. But then there is this third piece, or there's extra piece, which we will call the interaction. That has both p's in theta 1. And notice here there is only single variable, right? Theta 1 and theta 1 dot. That's one generalized coordinate, right? So maybe I should emphasize that by writing this as L1 is theta 1 and theta 1 dot. And L2 is theta 2 and theta 2 dot. Right. And interaction has the combination of the two. If not for this term, they will be completely disjoint. There will be two pendulums randomly moving about their individual points. Like they will be completely, this will be the superposition of two solutions. You know this solution, you know this solution, you know the complete solution. But this is what spoils the opening, if you want, or which brings in the richness. M2, L1, L2, theta 1 dot, theta 2 dot, cosine of theta 1 minus theta 2. Okay. So if you want to think of a two atom system, so typically how you see a system is, like think of a two atom system, or what is it, two state atom, right? Is that what's called? Two level atoms. Yeah, sorry. Yes. Yeah, two level atoms, right? Two level atoms is a very simplistic toy model of an atom where there are only two energy levels. Usually there is this infinite energy levels, but that's too much. Let's take a very simplistic system where there are only two energy levels. And let's say there is a photon coming in. So if not for these atoms, there is a system which is L1. They have their own nice little solution. L2, if not for the photon, L2 has a nice little solution, but when they interact, a lot of interesting things happen, right? Something goes from one to the other, or they can jump off and so on. And this is the interaction. That's an example I'm giving. This is how you would take this double pendulum and model a laser out of it. Like you have a laser where light comes in and something happens in the system, and it can have spontaneous emissions. Those are solutions you can have. And similarly, you can see such things in here. Here, the idea would be just that there's an L1, L2, and L interaction. This is just a very remote comparison I gave, but here the point is that this motion interferes with the other motion, or it affects the other motion. It couples them. So if this was 0, this is decoupled. If this is not 0, this is coupled. So that's the idea. Okay, so that's in your homework, you actually keep this to full cosine and sine for few more steps before you make the small angle approximation. But I'll do the simple things, you do the complicated stuff. I'll right away at this stage do the small angle approximation. So let's do small angle approximation. Small angle approximation, and recall that when you are doing small angle approximation at equations of motion, you can replace sine theta with theta and cosine theta with 1, right? That's what you do when you're doing it at equations of motion, but I'm doing it at a Lagrangian level, so I have to keep one more term. I have to go until theta square. Here I don't have to go because that's theta cube. Next term is theta cube. So let's do that. So then we have L1 is equal to half M1 plus M2, L1 square, theta 1 square, and this one is minus half M1 plus M2 L2 square, theta 2 square. And if you want, that is one more term, right? So it's half two M2 L2 square. What happened to the time derivative? What's wrong? No, because this is cosine theta, right? So there was no theta. So something is wrong here, right? Dimensionally. Oh, because this is G. Yeah, G times L2, right? I want to put G times L2. L1. Sorry. And this is G times but this is of course having no physics in it, or this doesn't contribute. I shouldn't say no physics. It doesn't contribute to any dynamics. Right? There is no time dependence. There is no velocity. So this is like uniform gravity. Right? So it doesn't contribute significantly to dynamics. So L2 is half M2. Yes. L2 square theta 2 dot square minus half M2 G L2 2 square plus M2. There is no half here. I changed the half here. There was a half, I deleted that because this there is no half. Sorry. That's a gravitational potential in uniform gravity, just because you're on the radius of it. And this is the interaction. Sometimes you call it L12. Yeah, let's call it L12 interaction. Or interaction, yeah, that's more. Sometimes L12 is better, but interaction first time when you see it highlights the fact that it's an interaction. That's equal to M2 L1 L2 theta 1 dot theta 2 dot, and here cosine theta 1 theta with 2 is 1, so I don't keep. Yes.
What happens with the 2 factorial?
2 factorial is this, right? Okay, I think I'm confused. So let's take this, right? M2G L2 cosine theta 2 is equal to M2G L2 1 minus theta 2 square over 2 factorial. So that's M2G L2 minus half M2G L2 theta 2 square. That's this term, the minus. Was that? That's what I wrote. Is that reasonable? Yeah. Okay. Clear? Okay, so yeah, so again, I should highlight that these are two independent systems, if not for this term. And again, M1, M2, no, that's only. Yeah. There are two independent systems, if not for this interaction term. They will be completely decoupled. And in this case, there is no simple decoupling, right? Because if you set M2 equal to 0, L2 also goes to 0. But often in systems, for example, quantum electrodynamics, when you do it, that can be completely split into a Maxwell contribution, that is the photons, and the particle dynamics, which is the Dirac equation. What is Dirac equation? By the way, have you guys heard of Dirac equation? No. Okay. So there is Newtonian physics. There's a quiz, right? So there is Newtonian physics, right? Which is true for V less than C, right? V very much less than C. Is that clear? Like when the velocity is very much smaller than the speed of light, then Newtonian physics works great. When V is of the order of C, when V, it always has to be less than, so V is of the order of C, then this is Einstein's physics, which is called the relativistic physics, right? Relativistic physics. I don't know, that's not standard. Can you guys think of any better word? Okay. The primary difference here is that kinetic energy, basically, or one of the primary, there's a lot of things that happen. Kinetic energy in Newtonian physics is how much? Half mv square. Let's write it in terms of momentum. So that's p square over 2m. Kinetic energy here, let's write it as energy, right? Let's say energy. Energy of free particle. Right? That's the kind. If there is no interaction, then it's the energy itself. Energy in relativistic physics is how much? mc squared.
Gamma minus 1 mc squared.
Gamma minus 1 mc. No. Yeah, you're correct actually. This is the kinetic energy. You're saying the total energy.
The total energy is gamma mc squared.
Oh, that's correct. But then it is now the gamma minus mc square should be no. So then you're doing E minus mc square, right? So then you're doing E minus mc square. That's not momentum. And then you will divide it by C, I suppose, right? That's not momentum. Oh, okay, let me write the solution, but I think you have it in your
Well,
mind.
starting with what I remembered and then
Yeah,
in terms of momentum.
Yeah, I think maybe the way I'm writing it, so, but if you said it like this, you surely know it, I think I can. But here is how you would say, this is the energy of a free particle, so energy and kinetic energy are very closely related. So here it will be p square, this is the momentum c square plus m square c raised to 4. Is that what you meant? Right, so, and like what you were saying is that E is equal to gamma mc square, and momentum is gamma mv, right? Then E minus P, gamma minus, let's see. I think, let's see. So you said E is equal to gamma minus 1 mc square, right?
Right.
So that's not P, right? If you subtract out that, you won't get this. Probably not. So let's see. Yeah, that's to be P, that's the velocity. Like this probably is the momentum of photon, maybe. But then photon will be having 1. Oh, that's the problem now. I think maybe I'm wrong, but correct me. Okay, later. I'm claiming that that's not kind of energy, but maybe
Well, it's you, if you modify it, if you substitute with momentum, you can get to the, because that's what that basically is the total energy minus the rest energy. Using,
I see what it's saying. Oh, I know what you're saying. Okay, I think that's the definition problem. Okay, this is not the kinetic energy. Then this is the kinetic energy plus the rest energy. But then you should get gamma mc square according to your definition, right? Let's talk about it. Oh, maybe here we should, right? Okay, let's see. Okay, digression. So what you're saying probably is the following. Okay. This is not kinetic energy in the following sense. Let's say E is equal to P square, right? So it is m v square, m square v square, and then 1 minus v square over c square times c square, let's say, plus m square c raised to 4. Like you would like to see what your, I mean, we wanted to subtract out this mc square, right? So pull out this mc square out. So this is mc square, and let me bring in the betas here. So this is m is gone, so this is beta square 1 minus beta square, right? And plus 1. All right. And this is nothing but is mc square. Yeah, maybe this is what you're trying to tell me. So this is 1 mc square 1 over 1 minus beta square. Right? That is gamma, correct? Good. Yeah, I think this is the point. mc square times gamma. Did you invented circles to prove this? Yeah, this was gamma. So that's gamma. But then you would say that that's your total energy, because in relativity, you have energy associated with mass. That's not kind. You want kinetic energy to be defined just purely out of motion. Right? So you want to remove the energy associated with mass. So kinetic energy in relativity, you will define as the energy of a free particle, no interaction, of something moving, but now you want to subtract out that energy, set t equal to 0 at mc square. You want to subtract that out. So that's gamma minus 1 MC square. Okay, I give up. I take back my statement. You're completely right. Yeah. So thank you. Okay. So I was making a wrong statement.
Move the camera just a bit.
Ah. Just a bit. Okay. Yeah, sorry about that. Yeah, but good. Thanks for pressing on it. But, yeah, okay. Okay, good. And what was I saying? Well, yeah, so let's get back to the point I was trying to connect here. Yeah. So Newtonian physics has E is equal to p square over 2m, only motion, right? This is a free particle, no interaction, no gravity or anything. There's no force, just a free particle. So if something is moving, it has an energy. Right? That's what Newton tells us. But now Einstein tells us that even if something is not moving, it has energy associated with it. Just because something has mass, it has energy associated with it. And that's the idea of an atom bomb, right? We call it nuclear bomb. If you can make the mass disappear somehow, there is energy associated with that. And it turns out that that's very easy because in a radioactivity, when uranium splits into two atoms, if you in that reaction, mass is missing. So I don't know the reaction asset, but if you take uranium, let's say, goes into, let's say, two atoms, A plus B. These are two smaller atoms. Right? All the protons and neutrons have to balance, and it turns out that first of all, this needs a neutron. Just to trigger this reaction, you need a neutron, maybe one or two, I don't know, right? So you trigger this, and interestingly, you get back to more than one neutron, or at least one neutron. All these protons and neutrons has to balance in all this, like atomic number has to balance, atomic mass has to balance. But if you calculate the mass on the right side and mass on the left side, this has more mass. So where is that mass coming in from, by the way? If both have the same mass, how can you change the mass? In chemistry, you do that, right? So mass is conserved.
It's the binding energy.
Binding energy, just because they were A and B were close to each other, there was this interaction energy between them. That was the energy. That's its energy in there, right? Because they were gone, now there is no interaction or significantly lower interaction, almost zero to our approximation. And that's the energy that is released. Right? That binding energy is so strong that, and that shows up as mass. So, or that is related to the difference in the mass. So just the difference in the mass is the energy that is released in that. But all that requires control, and that's where this neutron comes in. So that this is the trick now. Basic idea here is that if you have mass, you release energy, right? Even at rest. But to be able to control it, so the key idea between Einstein and the nuclear bomb is that you want to control it. And how do you control it? You use this neutron. This is not really one neutron, it's probably more neutrons on the right side. You have, let's say, 10 uranium atoms in a container, right? You trigger this with one neutron, but now it came out with another neutron. It will react with the next uranium. That will react with the next uranium. It's a cascade. Right? So that's basically a bomb. Whenever you have a small trigger kills or triggers everything, that's a bomb. And usually you have 1 gram of uranium, and that's sufficient energy. Horrific, but it's a neat idea in the sense that mass is energy. Very beautiful concept that we understand mass suddenly. But yeah, used in a very horrific way and very contextual, right? Very we are living through it today, right? Yeah, in a sense, yeah. All that was just a digression. Okay, we have energy associated with motion, kinetic energy. Here we have energy associated with motion and mass, but that's Newtonian physics. Speed is less than speed. This is approaching speed, but we do quantum mechanics. Right? Yeah. 2. Yeah. That's Newton in physics. Quantum mechanics, what does it do? Quantum mechanics, right? You start from energy, you switch it to operators, correct? Or better, you say that X and P is, you cannot measure X and P accurately enough, right? We mentioned that earlier, that X and P cannot be, position and momentum cannot be set up precisely, not because of our limitation in technology, it just cannot be done. You take it, there's a fundamental law that it cannot be done. It's not that it's a limitation of our technology. It's just not possible. Right? So that's why it's become the law. That's Heisenberg principle. And how do you go from here to there? There is one simple process, and that is to say that this is a very layman's or layman's way of doing quantum mechanics is you take energy and replace it with minus h bar over I and a time derivative. Right? You switch it to operators, right? And P is switched to what? If this is d by dt, what is this?
Gradient.
Gradient, very good. Yeah. So its momentum is switched to is related to position. That's gradient. And you get the Schrodinger equation. Right? If let me do this. Let me go there. So it is h bar over I d by dt at an operator level. That's equal to h bar over I gradient squared. It has to act on something, you call it the wave function. But it's just this equation that gives you that, right? So you would say that, okay, now we want to do relativistic physics. That means you want to do relativistic quantum mechanics. This is called Schrodinger equation. You guys know. Of course, no, this, right? What about relativistic physics? Do the same idea that h bar I d by dt is equal to square root. What does it mean to say that the square root of a differential operator? It's c squared. That's it, right? So, and it was, that's the layman's way of going from non-relativistic to relativistic. But then you need to know what is the square root of an operator, whatever that means. And it's not correct, or it has issues, and it was Dirac within 2 years of Schrodinger writing his equation, and Schrodinger and Heisenberg giving quantum mechanics. This is not correct. So Dirac came and said that this has to be done in a much better way. You bring in matrices, right? So how do you? Oh, let me not go there. Dirac equation. The Dirac equation is the Schrodinger equation in the relativistic case, right? So, and at some state you will see it, I think, in the last part of the quantum mechanics course, you should see it, I think, half a semester. Also, very interesting. The basic idea is the most interesting part is that the spin of a particle, which has no origins in the classical physics, becomes very natural in Dirac equation. In Dirac equation, spin is inbuilt. So what is the spin of a particle? Again, if you want to convey that in one line, how basically. It's an angular momentum of a particle when it is at rest. In classical physics, if something is at rest, what is the angular momentum? It's 0. But it turns out that it has. Right, so this comes out natural. So yeah. Okay, so all that is a digression for what? Where did I go? All
For the quiz question.
Yeah, but why did I go for the quiz question? I don't even know it. I was trying B less than C. Yeah, okay, I forgot. Better. But yeah, sorry about that wrong statement. Thank you for pushing thinking about it. Okay, so that's your in the last 6 minutes. Let me at least finish the equations of motion so that we can begin from there next time. Yeah. We have the Lagrangian now. Oh, actual Lagrangian. Oh, I didn't say that right here. So the actual Lagrangian here is L is equal to L1 plus L2 plus L interaction, right? So, yeah. Right. A decoupled system, another decoupled system, and an interaction. I think that's what probably led me to that. You have electrodynamics, you have photons, you have electrons. And yeah, that's what I was saying, that electrons are explained using Dirac equation. And then I asked you what the Dirac equation. So I was explaining that. So in the most sophisticated, very experimentally measured model that we have in physics is that of an electron. So this is an electron, which is Dirac equation. This is a photon, which is a Maxwell's equation, and there is a coupling between the two. This is called quantum electrodynamics. At a relativistic level, this has been understood, and experiments and theory has verified this to 13 sig digits. So that's one of the most successful theories we have, and that has the same philosophy. L1 plus L2 plus L2. When you think of standard model, you must have sort of standard model. They write, so there is a Lagrangian for one sector, electrons, Lagrangian for photons, Lagrangian for neutrons, neutrinos. One is weak interaction, one is strong interaction, one is electrodynamics, and then there is interaction software, which you can switch on and off. So it has the same physics in there. What is missing is the gravity, the fourth Lagrangian that we are not able to put in very properly. So that's the same physics. Okay, 4 minutes left. Once we have the Lagrangian canonical momentum, right? So this is P1 is equal to dL by d theta 1. We know that, so that's M1 plus M2.
For the interaction part, we don't use the second term
Where is the second term?
for expansion.
No, because there is already a theta 1, theta 2 in here, right? So that will be a fourth order. Right? Remember, derivatives also are an order, right? So it's a fourth order, so I don't have to keep it. Like if I keep it there, then I have to keep it everywhere. If I keep it everywhere, I'll get some physics out of it. But the first one itself has sufficient physics in it, so we don't even bother with it. That's what you will do when you're doing chaos. You keep the next term, and that will lead to chaos. Okay, so M1 plus M2, L1 square, and theta 1 down. That's your velocity, not P1. So let me say the total P, right? The total P will be plus M2 L2 square theta 2. No, I should be careful, right? We have a P1 and P2. P1 is this. There's nowhere else, but there is a contribution from here also. Right? So this is M2 L1 theta 2 dot. Correct. So there is a contribution to momentum from the interaction term. T2 is dL by d theta 2 is equal to M2 L2 square theta 2 dot, and that is plus M2 L1 L2 theta 1 dot. And that's it, I suppose. So my Euler-Lagrange equation will be time derivative of this has to equal to the derivative with angles, right? So time derivative of this will be m1 plus m2 L1 square theta 1 double dot plus m2 L1 L2 theta 2 double dot is equal to the Lagrangian with respect to theta 1. Theta 1 is only here, that's the only place where it heads, and it is minus m1 plus m2 g L1 theta 1. Do the same thing for the next one. M2 2 square 2 double dot plus m2 L1 2 1 double dot is equal to minus m2 g. Like a few more minutes, 3 or 4 minutes more. Let me divide out by m1 plus m2 L1 square. M1 plus m2 L1 square. The first equation that gives me theta 1 double dot plus m2 over m1 plus m2 times L2 over L1. Then there is theta 2 double dot. And let me write it on the left side. This is G over L1. 1. G over L1, remember, is the first pendulum's fundamental frequency. Same thing with the second one. Plus L2 L1. L1. Okay. Define few things. G over L1 is equal to the fundamental frequency of the first pendulum. Omega 2 square is G over L2. Say M2 over M1 plus M2. Let's say is alpha. And L1 over L2, I think this is what I call B. Hopefully it will either be this or the other way. So then your equations become theta 1 double dot plus omega 1 square theta 1 plus alpha over beta 2 double dot 0. Now second equation is theta 2 double dot plus omega 2 square plus L1 over L2, that's beta. This. The third term is a coupling. If not for the third term, these are two simple pendulums. So that's the coupling, and now we want to solve this equation. There are two coupled differential equations, and we want to solve them. We will be able to solve that for some initial conditions. Thank you.